Okay, everybody. Hi, this is 7.3. No, we're not going to do the entire 7.3. There's just one cool, awesome uh, proof I wanted to do, and here it is. So it has to do with symmetric matrices. So first of all, what is a symmetric matrix? Well, that's just when the matrix is equal to its own transpose. So if A is equal to A transpose, and you could kind of see if it's a matrix is symmetric, because if you go down the diagonal, everything is sort of symmetric across from the diagonal. Like there's the one matches with that one, the -2 matches with that -2, the 0 matches with that 0. That's B is symmetric. Um, C is not symmetric because the 1 does not match up with the 2. So it's kind of obvious what symmetric is. But there's a huge theorem. I'm just going to mention 7.7. I'm not going to prove any of it except for part of part 1. So if A is an n by n symmetric matrix, then A is diagonalizable. Now we're going to prove this today, but not. Oops. We're going to prove this part. This first statement. It's killing me. It's annoying. Never mind. We're going to prove this. This part right here. We're going to prove it, but we're not going to prove it for all matrices. We're just going to prove it for 2 by 2 matrix. That's what was case pretty much. But anyway, all the eigenvalues of A are real. None will be imaginary. And if lambda is an eigenvalue of A with multiplicity k, then lambda has k linearly independent eigenvectors. That is the eigenspace of lambda has dimension k. These are fabulously important theorems. It's called the real spectral theorem. And we're not going to prove it all. We're just going to prove part of it today. And that's what we're going to do really in this chapter. Anyway, let's take a look here. So we want to prove that if you have a 2 by 2 symmetric matrix, so it's going to look something like this. A and the main diagonal is going to be 2 different numbers or the same numbers, doesn't matter. And then across, then the other sides, you're going to have the same number, because this way A transpose and A is going to be the same thing. So if you have a matrix of this form where it's AC and then CB, and then again it's the same, the C here and the C there, it's the same number, same C. It is diagonalizable. So how do we show this? So we're going to start with the characteristic polynomial. Remember that's eigenvalues, eigenvectors, all kind of stuff. So we're going to look at the characteristic polynomial, lambda I minus A. And that's going to wind up being lambda minus A, negative C, and lambda minus B. And we're going to look at this determinant. And if you crunch it all out, you want to get lambda squared minus A plus B lambda plus AB minus C squared. Now we're going to use something that we learned a long time ago in, I don't know, whatever grade, 8th grade, 9th, whatever grade you learned this, I don't know, 7th grade, everyone learns this different times. The quadratic formula, yay! So in the quadratic formula, the discriminant in the quadratic formula, the discriminant is the part that's inside the square root. That's the b squared minus 4ac in the quadratic formula. But the b in the quadratic formula is actually the negative a plus b over here, and the c in the quadratic formula is ab minus c squared. So again, this is b squared is a plus b squared minus 4a is just 1 times c, which is ab minus c squared. So this is the quadratic formula. So if you crunch this out, you get a whole bunch of stuff here, and you wind up getting a minus b squared plus 4c squared, which notice is always going to be positive. Why? How does that happen? You get a squared plus 2ab plus b squared minus 4ab plus 4c squared. But the 2ab minus 4ab is negative 2ab, but that is a squared minus 2ab plus b squared. That's a minus b squared. The point is you have the sum of two squares, and we all know that the sum of two squares is never negative. Now there's two possibilities. Either it's going to be 0 or it's going to be positive. So let's take both possibilities here. Now, if you remember that, so because the discriminant is the sum of two squares, it's going to be 0 positive. So if the discriminant is 0, the only way that's going to happen is if A is equal to B and C is equal to 0. So my matrix, the matrix ACCB winds up being A0, 0A. Well, that is a diagonal. That is a diagonal matrix. So I don't have to prove it's diagonalizable. It is diagonal in that case. What if it's greater than 0? What if the discriminant is greater than 0? Well, if a minus b squared plus 4c squared is greater than 0, then that we all know that in quadratic formula, if the number inside the square root is greater than 0, that means that the quadratic has two distinct real roots. But we had proved earlier that in the last section that if you have two distinct real roots for a 2 by 2, that means there are two distinct real eigenvalues. And if it's two distinct real eigenvalues, we also proved it's going to be diagonalizable in that case as well. So it's all done. And this proof this, by the way, is the simplest of them all because it's a 2 by 2 matrix. This is the simplest, but that's the way it is. And it's all very awesome. That's all we're going to do from 7.3. This has been very fun and very awesome. And I cannot tell you how much I've been enjoying this. So we'll see you guys. I have to get back to Professor Snape just called me. I got to go down to his office. I'm not looking forward to that. But that concludes our video. And it's been a thrill making these videos and interacting with the fabulous students. Bye, everybody. Bye.